The climate thinking about energy, which would start at the beginning of a building's life, but from the story of the building's impact on the atmosphere, that story begins when we're extracting raw materials out of the ground or harvesting them out of the forest. And we follow the story of those materials, that first stage, just the product stage or cradle to gate, meaning the factory gate, the raw materials get extracted and then transported to a factory where they get turned into materials. And there's emissions at every step of those stages. We capture all that together, and that's the material emissions or the product stage or A1 to A3, all different ways of saying the same thing. Then those materials get transported to a job site and constructed. And that construction process can include temporary heating, and it can include all the equipment, cranes and so on and so forth. All emissions along that stage are also going up into the atmosphere. When you include all of that, those are the upfront carbon emissions, or the carbon footprint of the building on day one of its occupancy, or the pre-occupancy emissions, all different ways of saying the same thing. I like upfront emissions because it just makes sense, it rolls off the tongue. So that's when the keys get turned over and the lights turn on in the building. All of these emissions have already been released into the atmosphere, and everyone that participates in the architectural engineering and construction industry has agency over these emissions, right? We have demand side agency around what materials we're procuring and what we're asking for, and transparency. We can make decisions about using higher or lower emission materials. We can decide to start our buildings and construction in November or in April. So we participate in that, have agency in that. So that's within our scope to address, even though the emissions may be released, say, from a manufacturing facility thousands of miles away. So then we start the use phase. This is everything that happens during the building's lifespan. So use and maintenance, all your filter changes, every time you need to repaint your wall. If you're in, say, a retirement facility where the remodeling cycle can be like 10 to 15 years, that can be a lot of stuff happening in here. Or if you've ever been in a house that has the same wallpaper from the 50s, that could be a very small number. So, it depends. And there's also everything that comes from energy and water. It's happening at the same time, right, during the use phase, but we don't count the emissions associated with energy in the same total. So if you hear me say operational carbon, those are the emissions associated with all the energy usage of ventilation and heating and cooling and lights and plug loads and all that stuff. The energy usage happens at the same time, but we count it separately. That's why I was saying it's not included. It's not that's not relevant. We don't count it. We just don't bundle it up with the total life cycle emissions. Then the end of the building's life, there's deconstruction and demolition and transportation and processing and disposal. And that could be methane, it could be chemical release from blowing agents that were in the insulation in the building, and it can be all the energy that's emitted in all of that processing. You put that all together, that is the whole life cycle, or embodied carbon, kind of colloquially. But embodied carbon could refer to any part of this phase. And so we try to get a little more explicit so we know what we're all talking about in the entirety of the life cycle. We say whole life cycle, that's everything. We say upfront emissions, that's just before construction. We say material or product emissions, that's just what's associated, like comparing two products together. If I say operational emissions, we're talking about what's associated with the energy. I know it's a lot of terminology, but we're looking at a multi-100-year timeline with lots of activities. It's a little complicated. That's part of what we need to learn how to embrace in managing this topic. Maybe the last thing I'll say on this is the CO2e. So when I say carbon, that's actually sloppy language. Really, if I'm being accurate, I'd say the embodied carbon equivalent emissions, but that's a mouthful. So what we know is it's not just carbon dioxide is not the only greenhouse gas that's being emitted. There's methane, there's like a host of chemical soup coming from refrigerants and blowing agents and all sorts of, NOx and SOx and all the compounds. To be able to count them all with a single metric, we make their relative impact as a greenhouse gas relative to carbon dioxide and give that a value. And that's the E part of the equivalence. So for example, methane is roughly 30 times the intensity of carbon dioxide as a greenhouse gas over a 100-year period of time. So its CO2e value is 30. Carbon dioxide's CO2e value is 1 because it's 1-to-1 equivalent with itself. Does that make sense? Yeah. So whenever you see a CO2e value, that's looking at all the greenhouse gases, not just carbon dioxide. And that distinction is going to matter when we start talking about carbon storage. So instead of going up to the atmosphere, we're talking about carbon coming back to Earth. There is actually a difference there. So again, if I'm being a little like nerdy and technical off the gate, it's because I'm using a lot of different language, and I just want to make sure, at least if you want to look at this again in the recording or whatnot, At least getting the language accurate. All right, is that enough complexity for one slide? Let's wait. Oh yeah, please, yes, questions.
What's light blue versus dark blue in each of the?
Oh, great question. That is the error bar, so 65 to 80. It's extracted from another graph, so it doesn't translate quite as well.
Thank you.
Yeah, totally. Good question. Thanks for looking at the details.
I like shorts.
Okay, we're gonna get on. Great. This is awesome.
Do this.
Let's do this. Yeah, that was a lot of information. And yeah, please let's get some clarification here.
Why? I've never heard that operational energy reward is not counted for life cycle management.
Yeah, I've actually never seen it bundled into a singular number within whole building life cycle assessment convention. So for the brain trust that's looking at the whole life cycle, the operational emissions are always disaggregated, but almost always looked at together. So you'll see your ECOC is the common embodied carbon and operational carbon, and you'll see those two numbers like reported together a whole lot.
Is that because operational energy and operational carbon has been looked at extensively in some circles for a long time?
Yeah, and so there's different methodologies. There's a legacy of us having like generations worth of energy metrics and tracking and accounting and tools and whatnot. And there's pretty much just a conversion factor that's used to turn energy into operational carbon. It's like the grid intensity factor or the emission intensity of your propane or your oil. So that's almost always just a conversion from energy. And we have a whole world around looking at managing and evaluating energy, and the supply chains behind energy and the infrastructure that deliver energy are all pretty distinct from material supply chains and product supply chains and like the construction process ecosystem. I mean, it's related, but it's different, right? And so when we're trying to figure out, well, what's the embodied carbon of the energy, we're like looking at governmental reports of like energy emission factors for power plants and like what's the embodied energy of that installation. They're like going to the factory and seeing how much energy they used and so on and so forth. Like there's very different ecosystems, and so that's also part of what informs why we look at them differently, just the provenance from where that data comes from.
Right, there's a lot of people looking at operational energy in a lot of different ways, and you're saying we're looking at this other stuff that not as many people are looking at.
Yeah, like literally everything else but that.
Yeah.
Yeah.
Okay.
Cool. All right, next slide. Unless there's any other questions. Sweet. You don't have to remember all of that, as long as it kind of made sense.
There's not going to be a quiz at the end.
Oh, there will be a quiz.
Oh.
Yes, absolutely. Practice is actually doing it. All right, so I want to start looking at how we think about the operational body together. That was a perfect segue towards this entire next section. How do we think about those things together? So one thing we've done a lot of when I say BFCA, that's Builders for Climate Action, the team behind the BEAM tool. We've done a lot of modeling of operational embodied emissions of like many different buildings. We've modeled like hundreds and hundreds of buildings in different regions. In Toronto, we can say that like an average two-story house is using a mix of natural gas and sort of local utility electricity at a code minimum level of efficiency. It's releasing about 3.5 tons of emissions a year. So over 30 years, it's about 100 tons of emissions from the energy side. Excellent. And you can keep going. Sorry, too many animations. We know really well, as we were just saying, we really know what to do around managing the operational carbon emissions. We know to load reduce, we know airtight construction and super insulation and load management and efficient appliances and electrify everything. And we know what to do. It's just a question of like, how do we do that quickly and more? But that has a massive reduction of the emission profile after 30 years. That's like what, 80% reduction-ish? Quick math. Next slide. What we don't know, like actually go back one if you don't mind. Sorry, jumped ahead of my own narrative here. So the back arrow will work if you want to do the arrows. Cool. So the problem with this graph is that we don't start at zero. That's starting the middle or like a good chunk of the way into the building's lifespan. And from a carbon standpoint, over a 50-year period of time, we're already most of the way through the emissions by that point, right? So if we don't know what has already been released, we have no real visibility into like the majority, in many cases, of the emissions of a house between now and like 2050 when we're trying to hit these carbon reduction goals. So next slide, please. Time really matters, and we need to know what those upfront emissions are to make good strategic decisions around total carbon reduction. Because if we're only looking at the energy, we may literally be missing most of the building's emissions that we have agency over as designers and builders. And so the big challenge here is actually more like a framing challenge. Apropos of the conversation we're just having, I'm so glad we had that conversation. That's the illustration of this, right? We're used to thinking about energy. And for a long time, we've thought about energy as a proxy for climate emissions for buildings, which has allowed us to set goals and strategies for reducing energy and then saying, great, we're solving the climate problem. Except what we're finding is that's insufficient. It's not that it's necessary, but insufficient, as we would say in sort of research parlance. So yes, we need to reduce our loads. Like that's one thing we can say confidently, that like load reduction is like the #1 most effective strategy in both its value and its cost. But that also we need to know what those energy source emissions are. It matters if that heating energy is coming from propane or bunker fuel or natural gas or peak grid electricity or off-peak electricity or on-site renewable electricity. Like that matters to the atmosphere and to policy and to strategies and to technologies. And then also we need to know the material emissions that were up front if we really want to try to hit goals around our industry's contribution to the climate crisis by 2050. And the danger of only looking at electricity is we just miss all the other stuff. It's not that it's not necessary, it's insufficient. And we need to set the right goals to be able to get the right strategies in place for the limited time we have to take action.
So this may be a naive question.
No such thing.
What I don't get is the upfront costs are already spent costs.
When you say costs, you mean emissions or actual financial costs?
Emissions.
Yes, yes.
So why do we take into account if we want to reduce emissions going forward? Why do we need to take into account emissions that have already been released?
That's a great question. Because unless we're never going to build anything again, there's always another building that needs to get managed. So that's what we need to manage for.
Right.
And so this may get into a slightly philosophical or maybe like boundary question around the analysis,
Yeah.
which is actually not bad. So I'm going to touch that quickly and see if it scratches the itch. And if not, we can pin it. Yes, if I am accounting for like the emissions of the insulation material I'm putting into my building, it was manufactured maybe a year ago, it's already in the atmosphere. Why are we associating that to the building? Well, for a couple of reasons. One, that's the attribution pathway. So it may have already been released, but it's not going to, that insulation is not going to stay in the store forever, or we have a whole other problem. So it needs to get attributed. For attributing that onto the building level and to individuals who make choices, that's that path of attribution. So it may be that some of the emissions are already released, but you still need to account for them when our time scale is more than just time of use, which is the other framing issue with energy. We have a very fixed scope. We are looking at a building and while it's being used. And this is the hard part about life cycle emissions. We need to go backwards in time, maybe a decade, a number of years anyways. We need to go forwards in time, many decades. So think about what end of life means. Are you building a building that can be deassembled and reassembled? Are you building a building, spraying foam everywhere and everything that touches has to go into the landfill? We get to choose that now, but the impact won't be felt for 60, 80, 100 years. And then the spatial boundaries are like a landfill somewhere over there and a manufacturing facility somewhere across the world. So the math is actually really easy, but our temporal, our time and space boundaries have to expand tremendously in terms of what we're thinking about. Whereas energy, it's inside the building at the time the building's used. That's way easier to control the analysis. The math is actually harder with energy. There's too many more factors. Humans turning things off and on and sweating and the sun comes out. Energy modeling is hard, but it's can be very well bounded. I don't know if that helps answer the question, but yeah, thank you.
Just gonna add a little bit in that. When you're looking at an existing building and remodeling or renovating it, the other option is to tear it down, but it's already got all that embodied energy to get it to where it was. So reusing it and working with it is typically more conducive than knocking it down and starting.
And I think you're being too gentle. I would say it's far and away one of the most successful strategies you could possibly have in the built environment for addressing climate action is keeping our existing infrastructure vital and serviceable as long as possible so it doesn't have to be replaced. And there's cultural value to that, and there's a lot of pieces. But yes, 100%.
On that last chart, the one slide back, is this about the scale, right? Like that, the embody of 16 to 13.
Totally depends.
It's all these variable house to house to house, but is that in the realm?
Yeah, so I mean, I'm building a super high performance house, and I'm using like pretty like high emission materials to do it. A whole lot of high intensity plastic insulation, a whole lot of concrete, a bunch of steel, then oh, you could absolutely be dwarfing the operational emissions. If it's otherwise like a a clean grid, all electric efficient building. And we've definitely seen that. That's a
Well,
thing.
also like your prior slide had the operational emissions at around 104. Right?
Yeah.
Which we shrunk down to 13 by doing really great energy efficiency. Thumbs
Yep.
up to everyone.
Yep.
But all of a sudden, like the problem would be like that used to be the bigger part of the pie.
Correct.
So now it's the tiny part of the pie.
Yes.
Therefore, this big section that we're trying to recalibrate our calculations on and understand better.
Yep.
You know, that's why it's now more important because it's a bigger part of the pie.
And I'd say it's more important for three reasons. It's a bigger part of the pie now that we've done a much better job on the energy side. Two, you can be making that pie bigger if you're not paying attention
Yeah.
while solving the energy problem. And we're going to talk about that in a moment.
Parametrically sensitive.
And also, all those emissions are already in the atmosphere before you even turn the lights on. So we're flattening the timeline by looking them together in proportion. From the atmosphere's perspective, if I released emissions a decade ago when I manufactured that insulation, that's been doing a decade's worth of damage before you've even purchased it. And that matters if we're trying to hit goals within the next 15 years. So the time of emission has a huge value and magnifying value. And that's the risk of looking at over a lifespan. Is if, 10 kilos of emission here in the beginning, and then 10 kilos of emission at the end. I was like, those aren't necessarily the same from the atmosphere's perspective. The 10 kilos of emission in the atmosphere 40 years ago is year upon year upon year upon year upon year for 40 years doing impact. So that's the other reason that this matters. I'm already giving away all of my leads. Let's keep going. So
I just wanted to throw something in response to your question. It's a big world, and these are complicated equations. Our sphere of influence is only so big, but the work that these guys are doing is shining the light on one of the elephants in the room, and it's kind of been revolutionary. And there's a lot more steps to take, but looking at understanding the impact of the material choices we make is massive.
I'm going to tell you that story. And go one more further. Okay. Oh, so here you go. This one's for you. And I literally put this in because I'm like, some people want to actually see the numbers behind this. And here's the proportionality, right? This is like a selection of when we did 34 home benchmarking study in some small communities in British Columbia. We found, this is the average, and I'm not even going to talk about the numbers. You can look at the numbers. Everyone else look at just the proportions. There are absolutely some buildings with some really high emissions in both categories, like poor performing buildings built with really intensive materials. And then we definitely saw some buildings that were like, pretty modest in their embodied emissions, but were pretty leaky and under insulated and used a lot of energy. And then vice versa, we saw some high performance building with a whole lot of like high emission foam and some steel and stuff like that. And this, TLDR, you have to reduce across both categories to get an actual low carbon building. And this just gives some sense of scale and proportion and whatnot. But again, this is not time sensitive. This is as if this has all happened at once, and it hasn't. We're going to talk about time in the next chapter. You know what? Let's keep going because we're now just sort of getting repetitive and this is just going to be more confusing. Actually, maybe go back one. Let's just stop there. Rather than thinking of this as like the operational emissions tick up year upon year and then there's a crossover point at some point with the embodied. I see that a lot. I've tried to compare the two and look for a payback or a trade-off. We can talk about that. There's a whole conversation there. I'd rather not have it because I find it to be somewhat useless. For the same reasons we just saw, it's not until you reduce both that you get to low carbon values. If you're in a position where you have to try to like compare them to each other or like cut from one to feed the other or justify one with the other, you probably already lost control of the conversation. Like it's like trying to talk about simple payback for weatherization. Like if you're in that conversation, you've already lost the majority of the value of the work you're doing in the first place, which is health, safety, and comfort, dignity. Anyways. So it's also not what the atmosphere experiences. This isn't like physically accurate. So what's accurate is that you start here and then you add more every year forever as long as you're operating the building. So let's model for that and develop the strategies that respond to this type of modeling. All right, so this is where things get super interesting for me, and we can spend a long time talking about this, or I can move through it quickly, and it just depends on how many beers you want to order tonight. So we've been in the space of high performance construction for a long time and see a pretty standard palette of like, I'll just call them prescriptive strategies, like things you can kind of always do that you know are going to improve the building. And what we found in all of those, at a minimum, there's always a risk in almost all of these. There's almost always a risk of inadvertently increasing your embodied carbon emissions. You're consuming more materials, right? In pursuit of more insulation or getting a good air barrier in there or what have you.
Windows from you.
Getting a triple pane window shift from Europe, like any of those pieces can all potentially dramatically increase your embodied carbon in pursuit of reducing your operational carbon. And if what we're saying is we want to avoid this tension between the two, we want to avoid like creating one problem while solving the other. We need to evaluate both to find strategies that solve for the whole life cycle, that solve for both of those problems, if you will. And so what's really exciting is that at a minimum, there's almost always a way to mitigate the embodied emissions associated with an energy efficiency measure. Like, for example, you got to go to triple pane windows. Fine. Maybe you don't need wall to ceiling glazing. My apologies, architects. You could dial in the window to wall ratio a bit and hold some discipline around that as a cost saving measure that can also be architecturally interesting and satisfying, particularly from the interior, that can also reduce your energy loads, that will also reduce your mechanical distribution and your mechanical sizing, and then also reduce your embodied emissions as well. And so those types of strategies can be like analyzed and founded and looked at holistically and solved for both. We get the good windows and it's more comfortable and it's cheaper and it's just a little bit more modest in the glazing. That's just one example. My favorite one is reducing building size and surface area. That's another one of those win-win-win-win-win. For the same floor area, you can design a building with 16, 18 corners. I think the most complicated retrofit I did was my father's house, which had I can't remember, it's either 18 or 22 corners. I can't remember what we ultimately landed on, depending on what part of the garage you counted. Ridiculous, right? And not like, okay, anyways, so you get the idea, right? I don't need to like say a whole lot more about that. What we know is that costs a hell of a lot more to build. When I was in construction project management, we would often do our costing based on lineal foot of edge, not square foot of assembly. Our heat loads are greater through all the conductive losses at all those corners. It's hard to get a good air barrier. You got more framing, like on and on and on, right? So you solve that one architectural problem, and then you're also solving the additional waste issues of all the cutoffs that come from all those corners and the additional materials that need to be consumed for all that additional surface area. You're solving for all those problems with the same strategy. And that's the take home on this. It's recognizing we need to, one, expand our boundaries to think about more than just energy. We need to think about the actual carbon emissions associated with the energy and the materials, and then find strategies that solve across the board and don't forget a part of that or act like they're in some sort of competition with each other. That's the mind frame into making strategic decisions about our buildings that I'm inviting us, encouraging us, demanding of us to like wrap our arms around here. And we can keep going down the line, but the mechanicals are probably the most interesting part for me. I already kind of gave away the spoiler around that in terms of reducing loads, but could we go to the next slide? I think I say something on this. So I've just anecdotally, who has had an issue with oversizing heat pumps? Okay, well, I love that was just met with like a chortle, which is like a totally appropriate response to that question. It has been a really significant tension in our industry in the last 5 years of the decarbonization movement that's focused on the energy side, where we're trying to electrify everything, and heat pumps are God's gift to Earth now that they operate down to rated to -15, performing down to -20. They provide cooling in the summer. They have a great, efficiency. It's like the best thing since sliced bread. There's a bunch of significant issues though that we're having. One, the refrigerants that go into making those things work can be literally thousands of times the emission impact of a molecule of carbon dioxide. R410A is 2,100 times the emissions impact. If you take the lower emission refrigerants, that's like 700 times the emissions. I literally have had projects where there was a leak in the distribution system that basically wiped out a decade's worth of the energy efficiency value of that building before the building was even fully occupied, because they didn't turn the wrench correctly and get the appropriate seal on the flare dome. And I've seen that repeatedly. Right? So we need to open our boundaries. If we're only looking at the energy, there's no problem. It's just wins all the way across the board. Except once we actually start looking at the holistic impacts of transitioning that infrastructure, you see these ticking time bombs of upfront emission release from the refrigerants if they're not installed correctly. And so what we've also seen though is that the industry transition to go from just putting in boilers and furnaces, which are typically designed to be 2 to 3 times the load of the building because there's no penalty to doing so. They just chug along at 80%, 50 years, and no one cares. Now, that same strategy in a heat pump means it's going to short cycle. It's going to be incredibly uncomfortable, even during the heating season. It's going to be noisy. In the cooling season, it's going to be massively oversized, which is going to lead to dehumidification issues, which will cause mold and discomfort in the building and indoor air quality issues associated with poor dehumidification management. It's also going to shorten the service life of the equipment, so you're going to have to replace it more quickly and wipe out any of the cost benefits associated with the better efficiency. Oh, and they don't work as efficiently when they're oversized as well. So those great COPs that are advertised go down to basically the level of resistance heating. And that's what the industry has experienced when we're hurling incentives and trade support and just put everything onto heat pumps and everything's gonna be fine without thinking about loads and then everything else along the supply chain. Well, on the embodied carbon side, we're also consuming more circuit boards and more metal and more super intensive materials because we need a second or third or fourth compressor. Not to mention all the refrigerants that are now adding up in that additional charge. Let alone, now we have to have heads all over God's creation. Has anyone been in a building with 6 heads, one in every single goddamn bedroom? Right? And so now there's leakage points all the way along that distribution where the likelihood of having a refrigerant leak is now increased. Let alone the cost of a bigger and more expensive system. Let alone the fact we have to replace that entire thing over now every 10 years instead of every 20 years because we got our sizing wrong. So if we solve the sizing problem, we solve for every single other one of those like awful outcomes that I've named, from like industry transition to indoor air quality and mold problems to inefficiency to operating costs to first costs to refrigerant emissions to equipment emissions to replacement emissions, because we got the sizing right. Like those are the strategies that we need to identify and understand not only the benefit of those strategies, but the risks if we get it wrong. And this is why looking at embodied carbon is really useful. When we look at the life cycle, we can see where else is there another impact that we actually are causing intentionally or unintentionally when we make a decision around sizing the system or converting over to a heat pump before we insulate the attic or whatever. Sorry, that was a little bit of a soapbox. I'm in a home team crowd, so I felt like I could just go off. Anyone want to? Great. Yeah, please.
So there's sizing right and there's sizing with precision.
Mhm.
Two slightly different things.
Very, or potentially very.
And then there's sizing based on existing conditions. And then that is altered when you improve the building in 5 or 8 years.
Yep.
So, how would you advise folks to size a system if they're like, oh, in 7 years, we're gonna have the money to change the windows out for triple pane? Or,
Yep.
Or do exterior insulation now.
Totally. Yeah, that is maybe one of the harder problems to solve, which is a great one to talk about. Because if you can solve that problem, then you can get everything else right the first time. So if you have this is like, if you're in a commercial space, this would just be like capital improvement planning. But in the residential world, we're not used to thinking like in phases and staged development. So if you have a project where like, that's essentially what's happening, you can try and like bring the clients along into that type of planning. And if you can't convince them, like maybe do the windows first, or like the boiler's about to die, or whatever. Like sometimes you have to do things out of the optimal order. So then I would say if you have to put in heating improvements before you can do everything in the shell, I'd say there's 2 good ways of doing that. One, break things into zones as much as possible so that when you make improvements, you can kind of compartmentalize the system. And that just depends on the layout. Like it's, like sometimes that works, sometimes that doesn't. I really like having distribution systems that are much more flexible, like hydronics. I will go to the map for a hydronic system anytime when you need that kind of flexibility, because you don't have to worry about oversizing when you're just filling a big tank. And so if you need to, run that compressor less or retire one compressor, or maybe have 2 systems in parallel and one can go down, or one just then starts to be used as peak, and you got 2 systems that are maybe running so that they can continue to both operate even when the building's at a lower level, but they can be running a little bit more quietly. But that load can be matched to a hydronic tank, and the distribution can change however it needs to, depending on when you update that window or that room or add that addition. It's designing for that flexibility intentionally in the mechanical system design. And again, there's like, I mean, like two of my favorite ways, there's like a bunch of other ones depending on the circumstances, but just know the loads will change. What will they be? And what's the strategy for reducing either the how many systems are online or how much that distribution system may need to run. And that's all solvable. It's just engineering, it's just math. It's just we're not used to thinking that way. The technical solutions, there's a number of them and they're proven. It's the conceptual framework of like, oh, I need to design for that. So what will that load be? There's a strategy you can use, which is thinking forward to what does the future condition need to be. It will be super insulated. The loads will be calculated to X, Y, Z. And then backwards planning. So then what does that mean for my distribution? Or what does that then mean for my, again, walk yourself back to how you could change and modify the first design to arrive at the second design. That's just an engineering problem. And a good engineer could help with that part of it. But the planning part of it and getting the client on board with that, that's where I found most of the friction. It's like, nah, it's just too complicated. Just put in the big thing. And then like, cool. For a year, so you change your windows out and then you're bummed. And then there's all these other problems.
Yeah, I'm curious about how, like on the single family residential side, where, you know, the engineering costs that you may have to put into a project are pretty minimal, and you don't maybe want to engage a mechanical engineer for a 3-bedroom home at like 1,400 square feet. It's like where do folks get, like, who's helping them size these systems? Because I'm in a scenario where like ARC is definitely oversizing our system, and Efficiency Vermont is like, no, don't do that. But like, and then it's me in the room. And everyone's like, well, I'm like, listen to Efficiency Vermont, and everyone's like, I think we should listen to ARC. So I'm like, how you like, what's the compelling evidence to like builders and folks to be like, who has the best? It is
You
the
have to
engineer.
have an engineer.
I've resized like 5 ARC
Yeah, yeah,
for neighbors, just when I have that expertise, I just feel informed them. ARC, if you bid a 4-ton, this is actually a 2-ton.
Yeah.
Here's the minimum net. And I did accurately do that.
yeah.
The bigger question to me is, heat pump installers, what kind of training are they getting in load calculation?
So here's the thing. They're not.
Yeah.
And there is no functional enforcement of minimum quality standards for the residential industry around load sizing, around ventilation sizing, around ventilation, period. Like, this is not, it's so easy to throw contractors under the bus on this. And I get a little defensive over them, partially because that's a bit my background, but also because they're set up for failure. Like, the reason they oversize is because they've been trained for generations to manage the risk of people not having enough heat in crappy buildings in the winter. And now we're saying, no, shrink that margin of error from 300 down to 15%. But you still need to meet all the same expectations around, I'm never going to be uncomfortable. And they're the first person that's going to get a call on Christmas morning when it took a little bit too long, or someone left the window open, or blah, 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 and there's not the headroom and flexibility, right? Like, that's a setup for failure for an entire industry. So it's not a fair ask that they just like do the loads and get it right. I'm like, well, there's more infrastructure that's needed for that to work for the fourth owner who has never lived with a heat pump and is used to keeping their windows open because their the house is always too, whatever, you get the idea. We're building buildings within way smaller tolerances and margins of error than we ever used to, because we used to build them crappy and vomit fossil fuels at them to keep them dry and stable for 100 years. That's literally what we did. They would like sweat and have condensation all over the walls. We'd hurl ancient fossil fuels at them to dry them out and heat up this surrounding universe. And it worked. Those buildings still exist. And now we're like, maybe we'll do less of that. And then we realize like, oh, physics is real and buildings are complicated, and having a 100-degree delta T across a like 10-inch wall is challenging, right? Like, that's not actually easy. And so maybe we need engineering. Literally the entire rest of the built environment requires this, but some of our residences, it's just not relevant. And like, I'm just gonna swear, I'm calling bullshit on that. That's not like taking care of our own basic infrastructure with ventilation. Like, maybe we need air in our buildings and not just fire code. Like, and we don't even have a building code in this state because we think it's going to make it too expensive for our society to house ourselves. That's the most insane rationale I can possibly imagine. If you look at the boundary beyond anything other than the immediate first cost that you spend before you enter a building, that's supposed to last 100 years and keep people from dying. Like, who makes that type of cost decision? Well, we do. So it's not the contractor's fault. They're part of a system that is like set up for failure, and part of what we need is to invest in engineers and invest in better, infrastructure on our buildings, and it will cost more.
Yeah, and I think that's the challenge, like as Habitat, obviously, and working with low income clients.
Yeah.
They just don't have the money.
No, it can't necessarily come from the people that are living there. So then where does it come from? That's a much larger conversation that we are not gonna have right now, unless you want to stay here for a really long time.
In that conversation.
Get back to that one.
Beautiful.
Boy, did we go off script, which is awesome. We may just like put some of this slideshow for another night, but I'm loving it.
Actually, your question is like, when do you hire a mechanical engineer?
Oh yeah, let's get back to
To
that.
get things just right.
Yeah.
And we struggle with that all the time, and hopefully there will be a point in the future when you don't have to hire an expensive engineer for every project, and we know that this works for houses this size. And I don't know when that's going to work. We're going to arrive at that. But we clearly need to measure things a little differently if we want to get it right, if we care about efficiency. So there's all these externalities and these parameters that we're trying to operate within that are almost impossible. And how we shift that is kind of the question of the day.
And what I would recommend in your case, well said, did not mean to jump in right behind.
Oh, thank
That's
you.
very well said. Actionably, being part of the Habitat network, I would resource other Habitat chapters and ask where they've been able to get engineering solutions, because my guess is you're not gonna have to pay market rate for that. To your point, these buildings are not all that crazy different all the time. Like, we should yes,
Be a sense.
every building's a unicorn. Like, we moved out of custom construction because that's honestly not serving our society well, to think of every building as a precious little child. So yeah, sometimes you just need housing for communities, and so that's the market you're trying to reach. Like, you don't need to have it like precision engineered by some like top tier firm. You just need someone to run a manual J.
Yeah.
Like, talk to that guy. He's
Really?
got you.
Okay, I'm gonna give you that information.
Components of that, it's not just the heating loads we're talking about, we're talking about the building science of the humidity levels, the ventilation, the balance of. So these engineers aren't just looking at the heating cooling load, they're looking at it all, and the humidification, and maybe there's some humidification in the winter, and then the commissioning. So
That's
gotten so much more complicated, having somebody that understands it all work together on the team to make sure that when you deliver that product, we all work together. So that's we started with hiring engineers and all of it. Is to AFC, you don't throw in the bus. You get a project delivered and none of it's working. The airflows are all wrong. There's a world of missing and things will happen. So
We've had a lot of projects where just a valve is installed backwards.
Yeah.
And nobody can figure it out until the
Yeah.
engineer goes on.
Never.
The engineer comes on site, and even though you have folks who are reasonably well trained and do this a lot, they still can't even sometimes diagnose their own stuff. So, it's a little embarrassing when somebody finds it, stuff like that.
For critical services, that level of follow through is necessary. And the opportunity that you have is that if you're not building every single home custom, that's where you do that level of rigor on X number of buildings, and then it is replicable. That's the best advantage we have in residential construction. As someone who's benchmarked literally hundreds of residential buildings and has also worked in the commercial sector, you can get away with prescriptive approaches because the occupancy rates are very similar for most of these residential buildings, and the physics dynamics, everything at play. If you're not getting super creative with your building form and your material palette, like, it's not going to behave very wildly different if you're building the same thing more than once. And now that we've moved into production building and are now building kit homes, we're like, yep, they all kind of work the same. So maybe we don't have to model and engineer every single individual building anymore. If we're doing it, production home builders in the US figured that out a long time ago. The bigger question is, are we actually asking for the level of quality that we need? And I think that's the more important question that you're bringing up. It's not like, does this need to be really hard? Like, no, but it does need to meet all those quality factors. And asking is either going to be really hard and expensive or it's going to be crappy. It's like that's this reframing that we need to do the same way. It's like, well, it's either going to be like use a ton of really, intensive plastic materials or it's going to be crappy. Like, no, we don't have to make that choice either. It's a framing issue as much as anything.
I just want to point at something Jacob suggested, which is that actually you reach out to other habitat chapters, and I just, that work of connecting with other people that have already thought about this, that have a resource, that have maybe energy models that can say, here's a bunch of these that we've done for similar houses, you're good, or we've connected with this engineer who loves to give us pro bono work because of what we do. There's so much of that going on, and building those connections is a huge step that we need to take. We know this stuff. We just don't have access to the resources and the materials. So how do we break down those barriers? I think is a huge piece of where we're trying to get to.
The scale chapter, if we get there, will speak to that
yeah,
to some
sorry
extent.
about that.
But we can see how the evening goes because this conversation is awesome. You all are great. I'm having the time of my life here. Want to keep talking or should I keep going?
So let's see. It is 6:10. We usually stop 6:30 or later. I don't know how much time you need. I'm here all night. Yeah. When do people want to roll? What do we got? Aiming for the 6:30, 20 minutes.
I mean, I'll go until someone tells me to stop.
Okay.
I'm not gonna be there when they're selling that clock.
Yeah.
I go all night.
And some people I'm sure are on a limited
Pause
time.
at 6:30 to get people
Great.
step out on mass who needs to, and then those who want to just keep jam or jam, and then leave it there at their base speed.
Then I will keep rolling.
Okay.
6:30 you finish.
So someone call you keep moderating this. You're doing great. Oh, I should go back one. So then the last thing I'll say here. This curve familiar to folks? Have people seen
What does
this?
it say? Carbon reduction.
Carbon reduction potential over project stages, but just this concept of like early phase, late phase, good value, low value. I see this in cost estimating a lot. Like the best way to reduce costs in a project is early on in project design, where you have the most agency over the design outcomes and you control costs well. If you're trying to like do massive value engineering in like the early phase of CDs and like all this stuff like paint colors and trim, then like that's an expensive redo. You have to like spend a lot more money and time to go backwards to do the bigger moves. I see the same thing with energy efficiency. Has anyone in the passive house kind of space, high performance space on the design side and has heard from a client in DD, oh hey, can we make this a passive house? I have. That's expensive / impossible. But if we knew that heading in, it would be cost parity for all practical purposes at this point, like within squinting distance. So same thing with embodied carbon. Like if we get at this in the planning, you maybe even get to ask the question, can we keep the existing building? And if you get to ask that question, you get to make most of your impact because that is the highest lever on such this cascade of emissions that come with demolition and transporting all that stuff and site remediation and then re-leveraging everything that's needed for a new build. Like, oh my God, that's your high hand, but the building's already down. Well, you lost that option, and so on and so forth. 18 corners or 4 corners. Single stud with a plastic wrap or double stud. And then we get to like construction and procurement decisions. Like, you can be saving 20% of your emissions just choosing one brand of drywall over the next brand of drywall with no other distinguishing characteristics, because that's just how the manufacturing process. One was paying attention or one wasn't. We see the numbers. Those of us that are looking at the product emission numbers over time. Manufacturers are competing with each other for lower numbers. And it is a very active demand side pressure on manufacturers to have better product transparency for the ones that are in the sustainability market. And that demand is coming from us saying that this matters. So even just saying that, hey, give me a EPD for my insulation product sends a signal. That's a small signal relative to keeping the insulations already in the building service, right? So this is just like putting those strategies and like the potential impact you can have within something of like a time organized chart of like how much impact can you have the earlier on in the process that you intervene, which parallels that the carbon that's emitted earliest has the most emission.
EPD.
Oh, sorry, thank you. Environmental Product Declaration. So EPDs are essentially like environmental nutritional labels for building materials. So when I'm talking about the product emissions and we're looking at that life cycle, most of the information of that is coming from manufacturers that create a environmental product declaration sheets of sustainability declaration. You go on their website and click on it, and it'll say what the global warming potential was to make that product. And sometimes they'll tell you the whole life cycle. Sometimes they'll just tell you what the impact was to make it. And the tool that I built, or that we've built, that is the data behind the tool. We have thousands of different product declarations that are in there, and we just map out, well, what are the emissions of all these different products, and then give you a way to sort through it.
Who regulates that?
Great question. ISO regulations are the primary International Standards Organization. There's a very robust regulatory structure at the international level. Europeans have adopted their own. ASHRAE is now kind of like working with some of their own like North American flavors. But it's all coming from within like our like typical standards environments around how the EPDs are developed and third-party verified, and the standards that the reporting needs to match, and all that stuff.
So there is third party.
So the best the EPDs that I'm referring to globally are called Type 3. So they're third-party verified by a program operator that's following international standards on behalf of a manufacturer or an industry association. Yeah. Next. All right. Let's talk about carbon storage, because I think you all, judging by our last conversation, have the coins for this one. All right. Keep going. So let's start with the global carbon cycle, if you'll indulge me for a scale jump for a moment. I'm going to simplify this massively for the sake of, again, strategies and framing, if there's any takeaway from the orbit that I'm in right now. Carbon moves through our ecosystem into roughly 5 different pools in different directions and different intensities all the time. There's the biosphere where the plants are, the pedosphere where soil is, the geospheres where fossil carbon is, the hydrosphere. There's like 78% of all the carbon on the planet is actually in oceans. That's the hydrosphere. And then there's the atmosphere. And carbon is moving into and out of all of those pools in different directions, at different scales, and different rates. So it'd be hubris for me to like go any further than that. We can start from that place. Our way of thinking, our frame for how we address climate impact in the built environment has largely been represented from the left side. We are intervening in this global carbon cycle by taking these deep, long pools of carbon in the geosphere, this fossil carbon that used to be in the biosphere, it used to be dinosaurs and plants, and then over millennia has concentrated a long cycle carbon migration from on top of the earth down below the earth. And now we are intervening in the carbon cycle by extracting it, exploiting it for energy usage, and then the byproducts of that are cycling that carbon dioxide up into the atmosphere, causing chemical imbalances in the atmosphere, and also the hydrosphere. It's complicated. And our goal has been to do less of this. Goals are net zero, zero energy, harm mitigation, get to zero as a goal and stop doing that. And that is absolutely critical. Everything we're talking about with high performance construction, energy load reduction, and operational carbon reduction is all this, and it's all necessary, and it is wholly insufficient for the goal of trying to stabilize the planet's conditions for civilization as we know it to last through the end of the century. If those are the climate goals we're trying to set, not zero energy for its own sake, or for affordability, that's valid. For indoor air quality, totally legit. For energy independence and sovereignty over energy over infrastructure, fine, that's a great goal. For climate stabilization, totally insufficient. There's already too much carbon dioxide emission and chemical imbalance. And what we actually need now are strategies that fundamentally remove carbon dioxide from the atmosphere. It can't be going to zero. We need to can't just leave no trace. We actually have to leave the forest better, so to speak, from that old adage, right? So that's where this side comes in. We can, just the same way we're negatively intervening in the carbon cycle by accelerating this migration of stored carbon below the ground up into the atmosphere and the ocean, we can intervene in the processes of photosynthesis, which is the most scaled, proven, and cost-effective carbon capture and sequestration machine on the planet are forests. We have them. The only reason they're not uplifted more is because we don't give them an economic value. I'm not joking about that, but that's a whole other conversation we're not going to have tonight. So by intervening in the material space and the story of where materials come from, we get to participate proactively, not just harm reduction, but proactively intervene in supporting supply chains that support sustainable forest production and afforestation and creating more forests and sustainable agricultural systems and harvesting the waste products from these other industries and land-based industries to keep that carbon in the built environment. And we do that by making long-lived, durable buildings out of carbon that comes from plants that used to be in the atmosphere. And that's a way that we can intervene. We not just think about energy, but bring materials into the conversation, and not just look at energy, but look at carbon and carbon flows, and not just manage for our emissions, but manage for our potential storage and positively participating in these carbon cycles, that we unlock the real potential of what buildings can do in participation with ecological systems and not just in conflict or opposition. That's the thesis. That thesis is not just a thesis, it's backed up by a whole lot of science. This is a fabulous UN report that came out a number of years ago, 2 years ago, maybe just last year, that one identified building materials as one of the like crux intervention points across all industries globally to stabilize climate emissions because of the time scale, as well as the gross scale of emissions that come from building materials. But also that bio-based materials are one of the best opportunities we have for active decarbonization, by soaking carbon dioxide out of the sky, putting it into plants, and putting those plants into 100-year long lived buildings. Next. Sorry to intervene in the photo shoot. It's also not just academics and ecologists that care about this stuff. Really strong market signals around this. Amazon just commissioned last year a terrific report looking at sustainable wood supply chains for mass timber, because now the largest developers in North America are tech giants that are building data centers. And they are looking for ways to mitigate the harm associated with that real estate and infrastructural developments. And they're looking to their supply chains to figure out how to get that done. That is, I mean, yes, I'm sure there is a values or missions driven, interest in this, but let's be honest, this is a market signal around the value of these strategies. So I just want to be clear around sort of how broad this concept has already penetrated our industry. I'm gonna move through this pretty quickly, so just stop me if I'm going too fast. The way that Bills for Climate Action is sort of tackling this issue around, okay, so how do we take these strategies and account for them? Like what's the old adage in energy? You cannot manage what you cannot measure. And so we got really good at measuring energy. So we understood how to do better design and how to manage energy better. Same thing with carbon here. So, okay, how do we actually account for this in like appropriate ways so that we can come up with good strategies? It's very complicated with wood. It is not very complicated using residues destined for the waste stream. And so Builders for Climate Action has sort of disaggregated that. So instead of just saying bio-based carbon, we were looking at it in sort of two big categories: short cycle and long cycle. Short cycle means it's a short life cycle. We build a lot with straw in our company. That is a 1-year life cycle. There's no version after that, harvest cycle comes through for the wheat that it'll keep photosynthesizing for decades. Nope, it's done, it's dead. So we can harvest those residues. That's a no-brainer. Cellulose insulation. We're literally pulling carbon out of the waste stream before it goes into a landfill and turns into methane. Great, that's a no-brainer. Trees, maybe it'll keep photosynthesizing. Or maybe it'll be burnt, or maybe it'll be killed by beetles, or maybe it'll remain an anchor, keystone species in a complex forest ecosystem. Don't know. Depends on the forest, depends on the harvest cycle, depends on many other factors, right? Because it's a very long-lived, it's a long cycle product, 30 to 60-year harvest cycle. It's just more complicated. So the accounting and the valuing of that is more complicated. So we've broken it apart into these two categories. And this just helps us wrap our minds around the time scale and the different ways that we can develop strategies. So again, I work with straw a lot. It gets planted, it soaks up a tremendous amount of carbon dioxide over a 6-month growth cycle or so, give or take. Then maybe like 10 to 20% of the mass is cut off to become food, and the rest is waste. A lot of that gets burned, some of that gets anaerobically decomposed and turns into methane. A lot of that gets put into bedding or agricultural practices, but for the most part, it doesn't just keep photosynthesizing, it's going to hit the end of its life and go back up into the atmosphere. And we want to positively intervene in that short carbon cycle by grabbing that residue while it's still in, solid form on the planet and use it as insulation for our panels. And that's what we're doing. So we're all still, anyways, keep going to the next picture or two here. I'm getting ahead of I'm used to just smashing the forward button. And so that's how we are solving this problem of, or providing the solution of storing carbon in our buildings. We are using agricultural residues as insulation, or high-performing building products that are reducing energy and reducing the operational carbon, and also displacing plastic or mineral insulation that we might otherwise utilize. So that's another one of those win-win-wins. We're solving a waste problem for the ag sector. We're investing in regional ag. We are creating high value, high performing building panels. We're avoiding the use of highly industrialized insulation materials and reducing our operational carbon. Those are the strategies that hold the most value. That's why we're building with straw. Next slide.
Aren't you also supporting your local economy by getting straw?
100%. Investing in regional food sheds, especially we buy. Oh, I'm getting ahead of myself.
Yeah,
Yeah, we're gonna talk about that. So, you're bang on. Trees are more complicated. First off, do you start clock when that tree was cut? Or do you start the clock when the replanted tree replaces the one that was cut? And the difference of that is literally, maybe the life cycle of the building, like that could be 60 years. So do you have to replace that tree before you start counting that storage value or not? It's complicated, right? Long cycle. Next. Also, would that tree keep photosynthesizing or not? Or it's hard, you don't know, right? So it's more complicated. Also, because it's been undisturbed for maybe 60 years, the amount of carbon in the soil can easily be 1 to 3 times the amount of carbon that's in the aerial plants within a forest ecology. So if that gets all churned up with erosion and soil losses because of a poorly managed forestry practice, does that go into the accounting? It's complicated.
You literally like the root system doing that?
No, literally the soil.
Soil.
Yeah, but then also the roots, right? Because maybe only 50% of that tree ends up as the timber product. What happens to the slash? Maybe that's a positive contribution to the forest, or maybe it's slash and burn, and it's all just getting incinerated, and we're dramatically front loading the amount of emissions that are coming from the forest by burning it right in place. I don't know, it depends on the forestry practices, right? It's just more complicated when we get into wood in terms of how we account and value for it relative to the residues. Please.
You also have a comparative annual consumption rate of energy to harvest versus a 7,500 year consumption.
Yes, and so that's the other thing that needs to be looked at, not just the storage value, but what are the actual emissions associated with all those practices. And when you get to something like food and residue, that's where it gets really interesting. How much of those emissions from the that come from producing that straw do you attribute to the flower? How much do you attribute to the straw? I'm on a committee trying to actually define that. There's answers to all of this, but yes, it's complicated, right? And even that part's complicated. What's not complicated is that residue is going to go back up in the atmosphere if we don't use it. So we at least know there's a value there. With wood, it's just a little bit harder to predict, so it's harder to value. It's just more complicated. Not saying it's bad. I've harvested my own wood. I've worked in logging enterprises. I'm a huge fan of investing in local forests. In our region, the greatest threat to forest ecology is not industrial logging or illegal logging. It is actually development. So if we don't buy local forest products, those forests don't stay economically viable and they run the risk of land use conversion to development. That's our biggest pressure, not big logging operations, which is what you'd see, say, in Western Canada, or issues around plantation harvesting, which come in the southeastern United States, or illegal harvesting, which you may see in areas in South America or in Africa or in Southeastern Asia. Different problems in different, ecological and economic environments. It's complicated. Picking straw off the ground before it rots, that's not complicated. I'm not trying to be glib. That's how we were making some of these strategic decisions. And that's why we're breaking these into 2 different categories. Okay. Should I give some examples? Or do you want to go?
We are at 6:30 or 6:28, so close enough to call this.
If you want
for those who have to run.
It's all right. You gotta go now. No one's joining me, or else you gotta stay all night. Dylan, no, really? No one?
Who is this?
Bob Dylan. You can also leave in 10 minutes. You don't have to leave.
All right, let's give a round of applause right now.
This conversation is great. I never get this much conversation during my presentation. I love it.
Yeah,
Should I keep going?
keep rolling.
Cool, sweet. All right, next, we're gonna look at application now, getting all this heady stuff into practice. And we start with our company, because we want to have an opportunity to self-promote, but really it's because we have designed this company literally to be a case study for how to put this into practice. So it serves as a good working model of how we can engage, actually our transition from being custom design builders into fabricators and being able to have a direct relationship with developing a regional supply chain and being able to control those carbon flows very intentionally by developing our technical and business practices. So we are a high performance prefabricated bio-based construction company, 24 of us now. based out of Essex, Vermont. So we have our design shop, we have our retrofit, kind of weatherization decarb, existing building decarb team. We have a site team that builds our pre-designed, prefabricated homes within our region. And then we have our fabrication team that makes our panels, which we sell both as part of our kits, but we also sell as custom fabricators to other architects and builders for their custom projects. So, mental model of the panel here, it's a double stud box stuffed with straw. This is not complicated by design, simple by design. Double stud construction, instead of blowing with cellulose, we're compressing straw into the box. Other than that, it is essentially the same thing. We're just building those boxes in a factory and then putting up on site rather than building everything on site. So the way that works in terms of practice, since I know there's architects and builders in the room, we are on the Revit platform, so we are able to work with a full 3D architectural model, analyze that model, and basically create a panel layout for that model, and then convert those architectural models into it's a design to fabrication process. So we create the shop drawings directly from the architectural model for the fabrication team to build. So we get our primary vendor for our straw is the Aurora Farms, which is a seventh generation family farm in Charlotte. There's the farm behind the Nitty Gritty Grain Company, which sells like pancake mixes and flour mixes and bulk grains and whatnot in the region. So just to give a sense of the amplification of value, and us in using our purchasing dollars for the I don't know, hundreds of thousands of dollars of insulation materials we buy a year, we're choosing to invest that in a regional regenerative and organic agricultural producer. Now, the banks of Lake Champlain, which is one of the more polluted bodies of water and under some very strict federal, pollution remediation mandates. So we're investing in agriculture that's protecting an agricultural process, protecting that watershed. It's also one of the most gentrified parts of Vermont. So by investing in a working agricultural landscape, we're avoiding land conversion for housing, which would otherwise continue to burden the aging combined sewer and water plants all along the lake, which are also contributing to lake pollution. We're also investing in kind of like a keystone member of our regional food economy, because this is one of the only organic grain producers we have in our region. So we're psyched to be giving them more money and a value-added, investment in their waste products. So there's that immediate stack of economic, social, and also let alone the tourism dollars and value that comes from people driving around Charlotte and seeing the beautiful fields. And I'm not mocking them, it's amazing. I live in a place where people travel around the world to visit, and this is literally investing in the land management practices that make that possible. All of that cascades by our choice to buy this straw rather than mineral bath, or rather than some plastic insulation manufactured by some multinational chemical corporation, which we could absolutely do. We have agency over where we choose to invest as a fabricator. Maybe we're small, but I'm going to talk about what scale means in a moment. So that's the story of place around our insulation products. We stuff straw in boxes. There's one. We design them to be really easy to install in rural environments, as well as in urban infill environments, as ADUs and backyards. So we've created smaller panels that are more flexible rather than full walls or full modular construction. And that's examples of our new construction. We also design a line of 5 different pre-designed and sort of pre-built panelized flat pack homes. This is I think 700-800 square foot little home that's in the backyard of a house in Burlington. The family needed to expand. They couldn't afford to, actually the family was separating. They couldn't afford a second residence. So they built an ADU in the backyard of their home so they could both continue to co-parent and keep their family intact. And these are the types of housing solutions that we're finding needing to be infilled in today's housing market, and having these more flexible forms of housing solutions. We've done these for a lot of people that need to age their families in place. A lot of ADA accessible versions for mom or dad needing to come and live at home with the parents. So that's part of the social context around how some of this work can be done.
Is that foundation on a helical pier or?
Yes, absolutely. And so that solves a number of problems. It means that we don't have to get a concrete pump truck into the backyard in Burlington again and again and again. We save dramatically on the cost of the foundation install, as well as the logistics. It dramatically reduces the carbon emissions, which we'll talk about in a moment, and it helps bring in flood resilience for buildings that are in flood-prone areas. Win, 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 win. And yes, we have to like manage, water coming up into the building, and there's issues to solve there, but we prefer to solve those problems. Next. Pretty pictures. Also, health, super important. I don't care how low carbon the building is if people that are inside the building are getting harmed by the materials that they're surrounded by, or because there isn't sufficient ventilation in their home, so on and so forth. So all this carbon stuff I just want to name nests with a much larger rubric and a hierarchy of importance, in which health is a much greater value to me, in terms of the immediate value provided to the core stakeholders in this, which are the people inside the building. That said, we don't have to choose between those, and we choose materials that solve for those multiple problems. That's another benefit of working with bio-based materials. They are inherently non-toxic and healthy to both work with and live around, as well as being high performance, as well as being carbon storing, as well as.
Is that lime plastered?
Yeah, that's lime on that wall. We do a lot. We come from a tradition of doing plastered straw assemblies. That my first building was my own home, which I built 23 years ago. I raised the bales. And so we've carried that vernacular forward in our panels for clients that want it. Next slide. You can also make it actually go one more forward. It can also just look like a commercial drywall building if that's the appropriate thing to do. No one needs to know there's straw there if that's not comfortable. And now that we're expanding our market beyond the keeners, the enthusiasts, to more general markets, they actually may start to see straw as a point of risk. Maybe perceived risk. There's a lot of perceived risk around new things. Like, is it going to rot? Is it going to burn? Are there going to be insects? 3 little pigs. We've been culturally indoctrinated. So not trust anything that isn't sold by a multinational corporation. It can't be safe. So great, cool. We'll put drywall and fill paint on the walls. We're good. Nothing to see here. That's fine too. Commercial dining and kitchen facility using our panels for a farm in northern Vermont or northern New York, pardon me, just to show us commercial application as well. So part of the story for us in making this switch was actually not just we've been building with straw and trying to do workforce development around like building a industry of straw bale builders in our region for like a decade. Unfortunately, that decade spanned the recession, which, as everyone knows, you couldn't even find anyone to enter the trades, period, in 2011, let alone want to learn how to build straw bale construction. So we pivoted mid-century into prefabrication as a mechanism of being able to increase our impact in the number of houses we're able to touch and the amount of carbon we're able to store in buildings. That number, I think, now is over 500% in terms of the number of buildings we're able to provide by moving to a prefabricated model instead of custom building 1 to 3 houses a year. We've also been able to address costs significantly. We were getting incredibly frustrated that none of the members of our cooperative could afford any of our own homes. We were getting very frustrated that every single building was costing more than the last one, and the priorities associated with that sector of the market had more alignment around whether the grout was in the same horizontal position as the sill than the integrity and quality of the shell. And no shade against that sector of the market. I was just not meeting our company's social and ecological mission of providing housing infrastructure to our community, not bespoke housing for individuals. And so that was a huge part in us shifting to building these prefabricated and pre-designed homes, because there needed to be more cost-effective housing solutions for more people that weren't toxic. And we're now able to keep our per square foot housing costs to at or below $400 a square foot. We're going to see that going down as we continue to get more efficient with our manufacturing process. And that is for very small buildings. Typically, we see these small buildings, the cost per square foot goes up quite considerably. And this is, again, all electric, carbon storing, high performance, fully ventilated, all electric, spun unicorn fart type quality housing here.
And that's with finishes, or that's just?
That's finished.
Huh.
Yeah. Because I've designed the beam tool, I had a mechanism of actually being able to quantify this. Like, we are able to make decisions strategically because we were able to see what we were doing. We can now manage what we were starting to measure. So you're asking about the helical piers. One of our design criteria was, when we decided to design this line of homes, was that it needs to be carbon storing on day 1 of operation. We actually need to live out the vision around buildings being functional carbon storing vehicles, and figure out how, if anyone's going to do that, it's going to be us, because now we have control over the entire design. And so we did that in 2 primary ways. One, you can see the big negative bar here is yeah, I'm just going to there. This big negative bar is negative emissions from all. There's basically 6 metric tons of carbon dioxide that was photosynthesized out of the sky into the straw that literally that year went into the walls. And also, these foundation wall numbers are usually way out here because of rebar and steel, and concrete. And we were able to dramatically reduce that by using helical piers because we're building small lake buildings. We don't need 8 inches of concrete 8 feet below the ground to keep a little wooden building stuck with straw off the ground. It is unnecessary. It's also a liability in construction logistics and construction costs and flood risk and all these other pieces. So that ability to make visible the numbers could help us make very strategic decisions and employ these tactics that allowed us to achieve carbon storing buildings without sacrificing for cost or sacrificing for toxicity or sacrificing for these other values. And we developed BEAM explicitly as a mechanism for democratic data sharing. So much of the information that exists in the built environments is hidden behind expensive tools and expensive data sets and expensive engineering professionals that just run on energy, right? Like you just talked about the cost and tech and information and knowledge barriers to being able to just build good buildings. And it doesn't have to be that way. We literally built a spreadsheet-based tool by builders for builders, knowing they're not going to have access to BIM models, they're not going to know anything about life cycle assessment, but they need to be able to pull up on their job site iPad a Google sheet and go to the installation page and see what's going to be the best installation that I should pick up today. And that was the ethos behind this. Also, including the carbon storage values. Most of these tools don't give you these numbers. But now they're visible and we know the potential benefit if we choose to invest in these solutions because we can actually quantify and scale their value. The value is no longer invisible, it can be perceived, which also now means we get to include these materials that are invisible for most of these procurement tools. You don't find hempcrete and grass insulation and straw bale panels in most procurement tools. So no one procures them because they don't even know it's an option. This is an act of advocacy in making all of this information visible so it can be actionable and deployed. And that's one of the huge values behind doing this work. It's not just the number. It's the fact that there's even a line on the bar that shows there's a thing to value here. That's the reframing that we get to enjoy when we start opening. So yes, there's a burden. We have to think about more stuff. But look at all these amazing opportunities we have to work with when we actually start looking beyond the foam billet on the shelf. Oh, and this is just showing here, we disaggregate how we measure short cycle versus long cycle carbon. Got cut off a little bit there because of the screen. We automatically attribute this number in the net. We measure every single, all the emissions of all the materials. So you can see what's going into the atmosphere. You can see what the potential storage is. We do the math to show you what the net is and apply that to all of these short cycle materials that there's no version where it continues to photosynthesize in a forest. But wood's more complicated. Maybe you need to like know where that wood came from or get an FSC certification or know your forester or what have you. So there's a click button that the user gets to choose to click or not if they want to apply that value. But the value is shown anyways to incentivize you to ask your lumber provider to supply FSC certified wood because you can see what the value is and you know that it's important. And that gives you, the designer or the builder, an opportunity to value that and then give a demand signal to your distributor to ask for a better, cleaner wood supply product. And that's why Amazon released that report. Literally this process, what is the value and how do we create a demand signal so there's value in the manufacturing sector to make better, cleaner, more transparent wood products.
Amazon did that report?
Yeah, that was the one I pointed to earlier.
Okay.
Yeah.
Are they good or bad?
Yes. I'm not a big fan of binaries. I'll just say that.
That's fair.
So some really quick case studies. If you want to get lost in the charts with me, I'm here to go all night with you, but I'll keep this high level for the rest of the crowd. Not just small little buildings like new frameworks. I'm just going to show you a couple other examples of scale of building typology. Here, we built a university lyceum. This is offices and classrooms and lecture halls with double stud cellulose insulated wall assembly. It doesn't just have to be for small detached single family residences. This is actually the second one that this firm Bruner Kott did in the was the Five Colleges area around Northampton. Sam? Yeah, this one's Amherst. Yep, they did another one like a couple of years prior for another one of the ones, Holyoke. No, what's the alternative school down there?
Hampshire.
Thank you, Hampshire. They did an amazing center for Hampshire using the same wall assembly. We got put through the ringer on this from Amherst third party enclosure commissioner. Both in design, they literally said this was illegal. And then we had to go through a whole defense case of the hydrothermal properties of a double stud cellulose wall to prove that it was not going to rot out in this building type. And we proved it, and we put a whole bunch of sensors in the walls. And we actually built the walls in two different ways with vapor retarders, both in the middle of the wall as well as in the interior of the wall. The Hampshire College project had no vapor retarders, so we have 3 different wall assemblies to compare in institutional construction using double stud cellulose insulated wall assemblies. And you know what we found? Freaking boring. Flat lines below 18% in every single building forever. I'm being a little dramatic. Actually, I'm not being dramatic enough. Some of them are significantly lower. There was literally no functional risk of any moisture problems within any of these wall assemblies after years of operation in an institutional context. So can we please stop saying that you can't apply these things into larger scales? These are the types of reframes that we need, and data can help us arrive there. Next. Also, North America is way behind most of the rest of the planet in learning how to work with bio-based materials. I mean, way behind. So just looking at Europe as our most close counterpart in terms of comparable level of industrialization and economy, we've got one of literally dozens and dozens and dozens of public schools across France that are built with prefabricated straw panels, mostly for their health attributes. And that's just France. There are now, I think, thousands, certainly many hundreds of straw passive houses across Europe, let alone other types of construction. Lots of different apartment complexes all across, in Austria and Scandinavian regions. This is another one in France. Sports facility in the Netherlands was retrofitted with blown-in straw as part of a retrofit project. I have another slide deck that has about 12 of these large institutional and commercial projects. This is the biggest one. I'm just gonna go straight to the largest one. This is like a 1.7 million square foot logistics facility in the Netherlands that was just built with compressed straw prefabricated panels. It's very similar to the ones that we're building, and mass timber. This is not a technical problem to solve. This is a cultural problem. And with a lot of structural barriers that have been institutionalized by dominant industries in North America. That's the problem to solve, not, but won't it burn? No. Nope. It's not gonna burn. It's gonna burn way less of a risk than all the foam that is in all the North American counterparts of these buildings.
Is there a denaturalization process or dehydrating or
Nope, compression.
mediating?
It's like trying to burn a telephone book. Straw has a class A fire and smoke flame resistance rating, unplastered. And I've been involved in tests where you're just literally blow torching this bale and it just chars, kind of like a timber. Cellulose and lignin, it's the very similar physical properties as to wood.
But it doesn't get packed until it reaches a certain dehydration level or something?
Oh, yeah, start dry, stay dry. So yeah, we make sure the straw is dry when it's coming out of the fields. We work with farmers that manage for the quality of the bales and their cleanliness, their dryness, so on and so forth. And we have a rigorous quality control management practice around starts dry, stays dry until enclosure. And there are some risks around bringing prefabricated insulated panels onto a site before the roof is up. So that's a very relevant question in terms of how do you manage through the construction process.
We're nowhere near it, but is there eventually a feedstock availability to scale of install this bench?
Wait, ask that one more time.
Is there a feedstock availability? How much feedstock of straw could there be if we actually?
Oh, every year we could build all the housing in India.
Yeah, that.
Oh, really?
We have that's wheat straw alone.
I assume not,
Yeah,
that comes
no.
from the biogas world, right? Like,
Yeah.
like
100%.
if we're gonna start putting, renewable natural gas into, like, no, don't do that. There's such a small feedstock for that. Use that for a higher priority.
And here's the irony, actually, one of the large contributing factors to global greenhouse gas production is methane production from agricultural residues.
Yeah.
So this is that, like, we
Yeah.
can solve that problem. In Northern California, in the grain growing regions, they're literally flooding fields with the water they can't afford to use to anaerobically decompose the straw, making methane plumes because they're not allowed to burn it because of smog control. This is the level of insanity that we are facing in terms of trying to coordinate these residues. There's no shortage of residues to build these. We're not going to run out of straw before we run out of housing. That's right, primarily rice production for human food markets. Yeah.
You must be a vegan.
What's that?
You must be a vegan.
Me?
Yeah.
Oh no. I was. I'm a recovering vegan. Yeah. There's a whole value stack here. I think as I was pointing out, we've already talked about this, all these values. I think we're getting close to the end here. Keep going. I am going to show you, I now want to talk for a moment about scale. We talked about scale and like you can build $1.7 million facilities. Like that's useful for a whole bunch of reasons around industry transformation. That's not super relevant for most of us trying to make cultural change or industry change or regional change in the housing sector. So Beam comes preloaded with a model of the Department of Energy model home. Like typical American home happens to be like 2,400 square feet detached home. So that's modeled in Beam. And you have to click a couple of times here. Sorry to interrupt you there. One more time. Great, stop there. So we looked at like business as usual building with like typical, concrete and XPS foam and, all the trimmings. And a typical building would be like roughly 33 metric tons of emissions to build. If we optimize that building to store as much carbon as possible using, market viable, this is, we're not defying the laws of physics or inventing materials that don't exist. This is all market ready materials and published transparency documentation. We could be storing 6 tons of carbon in that building if we're optimizing, designing for that explicitly. So we are all now in a place where we are facing massive housing crisis within our region and huge pressure from the top and the bottom to rapidly build out large volumes of housing. So that then begs the question, if we were looking at, we did the math, we kind of contacted all the different states, we looked at state reports and what their housing estimates of build out would need to be to safely house our communities between now and 2040. So like 2 million units of residential construction. So if we were to do that, are we going to find ourselves in the exact same dilemma around creating an embodied carbon plume in pursuit of our operational energy reductions? Can we solve our housing problems and our climate problems at the same time, or are those inherently in conflict with each other? We have to click a couple times here. So the worst case, it's like putting 20 new coal-fired plants online between now and 2040 to build out our housing needs, if we're not thinking about the material impacts. And that is that's the equivalent of having that refrigerant leak in your heat pump eradicate a decade's worth of energy efficiency value from the high performance house you just built. Or if we optimize for both in the best case, we could be taking almost 4 power plants offline while also providing all of our housing solutions using residues. That's like the span of the outcome and also the impact of just that low-rise residential construction, right? I mean, granted, some housing is going to be high-rise and mid-rise, and I'm oversimplifying. You get the idea of the potential of scale here. Let's move on. Okay, you want to stop there? I have a bunch of resources I can spin through in like 10 minutes, or you can just tap out. You're done.
You want the resources.
Okay, I'll go through this quickly. Stop if you want to talk. We are very close to the end. So this is where I bring it back up to the level of like standards and policies and stuff that I've been working in. So like a decade ago, I'm going to be like a little oversimplifying here, but like basically for a decade ago, basically all this work was like in academia. There's like a couple of tools. There's like a few like super niche, like eco-minded architects working with like an early version of the Athena calculator, but really this was like an academic exercise a decade ago. And now we are at the point, actually I have to look at my slides here, we have within a decade developed an initial sense of scale and like that piece like how bad is bad? And all like basic known prescriptive hotspots around where the most carbon shows up in these buildings. Now there have been thousands of benchmarks done on thousands and thousands of buildings across the world. We have like very clear prescriptive actions that every sector can take to immediately reduce their emissions. We've got a whole battery of very sophisticated modeling tools to be able to do predictive analysis on new construction and retrofit scenarios. And we have tools and information up the wazoo, more than we can actually handle as practitioners, more than we can even learn, right? And that's where we've come in a decade. Compare that to the fact that the first airtight building was built in 1972. And we're still trying to fight for air ceilings. And we're still trying to fight for an energy code. We actually saw the energy code go backwards in the state this year. So just to give some point of reference of how rapidly we are transitioning this industry to embrace these concepts and change our frame and bring materials into the conversation, right? So we're now in the place where we're developing uniform standards around how this work gets evaluated. So is everyone familiar with ResNet and the HERS index? So if you aren't, so ResNet is the largest energy rating system in North America. There's over like 4 million units that have now been energy rated. They're now starting to be bound to like real estate declarations and things like that at this point. So we are on the verge where I'm on the technical committee looking at standard 1550. It's an embodied carbon standard for energy raters to do an embodied carbon assessment at the same time they're doing an energy rating. Something like 80% of the inputs going into an energy rating, those are all just building area inputs. All of that can be applied towards doing an embodied carbon assessment. You need a few more bits of information around the materiality, see what the insulation is, not just the R value, and then you can functionally produce an embodied carbon assessment at the same time you're doing an energy model. So we can leverage this entire existing infrastructure of energy modeling and do it with people that can actually look at both of these problems at the same time, built into their analysis, not having some additional expensive engineer or consultant need to do that in the residential space. That is going to allow us to mandate reporting and get some regulatory practices in place and actually be able to migrate us at scale across industry to be able to manage carbon and get towards carbon storing buildings at industry scale. This is like the birth of understanding what energy metrics are in construction. That's where we are right now. So incredibly, these things are happening. It's going to spin you through a couple of the exciting things that are happening in case you want to get involved or learn more. I just explained what ResNet 1550 is. I totally jumped ahead of my own slide. Yeah, keep going. This has already been piloted. We had a 100 homes benchmarking study we conducted last year where we both surveyed 100 homes so we could create a regional benchmark for North America, which is the first step towards being able to create incentive programs. There was a utility that almost created an incentive program this year, but is now going to need to wait for one more cycle, literally building up the benchmark that we created by surveying those homes. We also trained a whole whack of HERS raters to do this, as well as road testing the standard itself, as well as road testing QA/QC procedures so that we could get industry preparedness like ready to functionally conduct these assessments at scale. And as a tool provider, I was able to work with the energy modeling company, energy rating software company, to figure out how we can make it easier for the raters by having our two pieces of software communicate and dramatically reduce the time and the cost associated with those assessments. We did that within one pilot already this past year, and now we're leveraging that for additional pilots and additional build-outs. So it's not just about having the standard. It's about having a standard that actually has software that can make the standard usable by practitioners that are already in the field doing this assessment work and binding those results to energy reports that are already going out into the marketplace and being associated with real estate values. It's all of those things happening together that enables this degree of scale change, not just the technology or just the metric or just the tool. So most of my work right now is redeveloping Beam from a Google Sheets to a national compliance tool, both in Canada and the US, for two different methodologies and standards of how we conduct embodied carbon assessments at scale in the residential sector. No problem. But that's literally what we're doing right now in real time and will be released next year. A nationwide compliance tool standardized across the industry for how we do this and share that knowledge and share that data in a standardized and uniform and consistent way across the whole ecosystem, not just people that happen to be using this tool or that tool. Same thing's happening in the non-residential space. ASHRAE is working on their own version of that that's going to apply in the commercial sector that is a combined operational and embodied standard. So it's looking at both of those and standardizing how do we do this evaluation in the commercial space. I'm going to call it MEP 2040 MEP 2040 is a group, it's a collective impact organization of a group of mechanical engineers that really care about this stuff. All the stuff we're nerding out at the beginning about heat pumps, folks for whom that is their daily job, have volunteered, bound together, and created a best practices guide on how to manage embodied carbon within mechanical, electrical, and plumbing, which has been way behind a lot of the rest of the industry because it's so complicated. That information has informed the standards. The standards are modeling the practices that scrappy groups of volunteers that really care are developing their own best practices, which then create a generative feedback loop that practitioners are informing standards, which improve best practices, which can scale across the industry, which bring more people into contributing into the solutions. And that's how this is happening. It's not, unfortunately, there's no federal leadership guiding this. It is literally collective impact groups of motivated practitioners saying, nope, this is how we do it. The same way we had Beam, we said, nope, this is how we count carbon. And now short cycle carbon is a defined metric in multiple regulatory statutes in Canada. So we said, yep, that makes sense. So you need to count that and you get value for that. Because we said so, right? We're at the point where we actually get to define our work. This is incredible. This is about as democratic as it gets in terms of changing the face of industry and how we value the work that we do. So there are many organizations that, yes, you too can join to participate and not only find some camaraderie and some support and solidarity and knowledge sharing, which is crucial when you're trying to do this transformative work in what is a very hostile political and economic environment, but can actually functionally do the work that all of this developing standards and best practices is built upon. So the ECHO Project is a volunteer organization of multiple different organizations across the entire built environment and horizontal infrastructure sector to come together and agree, here's the standards of how we're going to assess carbon. Like literally building a schema that says, are we going to report on the whole life cycle or just A1 to A3? Do we just count structure? Do we also count the finishes? What do we do about biogenic carbon? This is normally the thing that people guard behind IP walls and defend to the teeth as their own proprietary value in the market. No one has the best standard but us. No one knows how to count carbon like we do. This is a whole bunch of organizations saying we're all going to do this in the same way to help actualize industry transformation. That is not how this normally works. And any one of these organizations themselves are radically collaborative, and a bunch of practitioners that otherwise would be competing with each other about, no, you can't look at my design details. I have the lowest carbon project and I'm going to win the next bid. No. Literally sharing best practices of how to collectively manage carbon and collectively act with a singular voice for the demand signals to manufacturers. Just give us the information, let alone come up with solutions based on the best practices. So if you're in landscape design, if you're on the contractor side, if you're an MEP engineer, if you're a structural engineer, if you are a laboratory engineer or designer, urban land planning, international sustainability, what else we got? Plumbers and associated trades, infrastructure designers, LAs. There is a collective impact organization for you, including those of us that are in the low-rise residential sector. Keep going, because I think that's the next slide if I did my job right. Right. So there is less collective organization in the residential space. That is a power BS and beer, is this is some of the most like potent grassroots collective knowledge sharing groups that I have found. And the fact that I get to speak about this stuff in a building science environment, I do not take for granted, because I've spoken to some very hostile building science crowds before. Not everyone cares about this. Spoiler alert. So there's a couple of organizations regionally which I'd strongly recommend. I'm one of the steering committee members and co-founders of the Bio-Based Materials Collective. This is not just builders and architects and engineers, but also people, academics, people in the forestry space, some agriculturalists, people in manufacturing, supply chain folks that are all working on these systems level problems. How do we get more bio-based materials into the built environment? Super nerdy, super fun, very eclectic group of people across North America, but a huge home here in the Northeast. Join us. Also, the Carbon Leadership Forum, which I mentioned, they have regional hubs and meetups. This is maybe a little bit harder to access for those of us that are more in the like rural residential construction space. but there's a ton of knowledge and information and resources. It's more urban architects, it's more Boston based, but they're really trying to figure out how do we reach out to our counterparts across the Northeast and across the trades and so on and so forth. So they're a phenomenal group of very driven people, and just the resources that they published on their website alone hold tremendous value if this stuff is of interest to you. From like a whole 101 series to a whole lot of dense information on a host of topics from policy to practice. Okay, I'm going to wind this up with some nice metaphors here. Last couple of slides. So this holds some value for me for a couple of reasons. One, it is so easy to get lost in the weeds in all of this work. It's so easy to get confused by life cycle assessment and which tools to use and how to think about this. I recognize how overwhelming this is, and there's a lot of risk associated with that. So a couple of things. One, we're doing this because we come from places that we love, and we love people that live in those places. And that's the point of all of this. And having some North Star around that and naming that is actually super important. One, so that we're not just focused on an energy metric and forgetting the other things that we care about and that are important to us. But two, because often right now it feels like we're literally going backwards. And for everything we've built up over the last ever many generations, much of that feels like it's been erased or like turned back in the wrong direction in the last 8 months of energy policy and immigration policy that directly affect our industry. As a paddler, I'm used to being on a river and then literally going on an oxbow and going back in the direction I came from. But it's not scary or disorienting because, like, we've looked at a map, we know that that river leads towards a place on the other side. The hard part about this work is we don't have a map. Transformational work is by nature emergent and non-linear. It means it's not going to ever be a straight path between where we are now and this like horizon that we know we want to arrive at with carbon storing buildings. It will never be a straight, clear path. And we are not going to know what obstacles we're going to face around the oxbow. We don't know what's going to happen in an election in 2 years. We don't know what's going to happen in 2 days. That's going to dramatically, change material pricing or market, wins. So the way to do that is to have clarity around a North Star and to understand that our best strategies are around flexibility and adaptation. And whether that is knowing that the project path may not be linear, enclosure first, reduce your loads, then size your system. It's going to be non-linear and probably emergent because it may be the third owner that ends up changing out those windows. But if we can create adaptation strategies around if then, and here's how you break up the zoning of your project, and here's how you phase into that, it allows us to get to that correct end goal when that third owner changes out and finishes the scope of work. Below that out in scale in terms of an industry transformation, trying to figure out how to get off of petrochemicals for every single building material that goes into our homes into a much more generative and broad and valuable set of materials. It's not going to be linear, and we're not going to know what headwinds we face until we turn the next corner. But if we have clarity on what that endpoint goal is, then we'll be able to adapt and flex successfully and make sure we're still ultimately heading in the right direction, even if sometimes it feels like we're going backwards. And the last slide I'll leave you with is that we can't get there by ourselves. And the reason we've been able to get the traction that we've gotten around the transition of materials and the daylighting of embodied carbon as a metric to plan around and value and economically support is through collective impact and working together in radical sharing of knowledge and resources and information and having collective demand signaling to the industry that this matters. That is literally what built EPD development from the manufacturing sector. I have interviewed manufacturers and research projects repeatedly, and they said it's because LEED required EPDs to be provided on projects, and so we started producing them. And we'll do that for the residential sector too, as soon as there's demand. And that's what I've heard again and again and again. And the metaphor here is that we see these huge, large trees, some of the largest organisms on the planet, and they look like they're disconnected and kind of holding for their own. But what we understand is below the soil, there is this entire network of relationship between these trees and this whole community of mycorrhizal fungi that are transmitting and transferring information and nutrients and resources across this vast web of species that now work collaboratively and collectively to stabilize an ecosystem. And that is the model for how we are in real time creating transformation within our industry. So I hope you join us. Thank you. Stayed very long with me and I really, so.
Thank you, Jacob. Thank you, everybody. That was fantastic. Hope you all come again next month. Really appreciate everybody coming out tonight.
That's the, like, yeah,
Sitting the whole time going like, what all this stuff? The pressure.
pressure in the box. So there is there are good folks in California that are building their own version of the nails out in the woods. And they want to get complete. So the niche developed a proprietary bio-based binder to have bound, like a bound strong interest to create their. And so those are the types of technological solutions that are going to leverage off the work. One thing I didn't even mention tonight is that we're not actually building these panels ourselves, we're actually starting a network of fabricators across North America. We're co-fabricating off the same models and using our sort of collective investment, R&D, and testing and standards development. We're all building off that simple box model because it's a very low point of entry. You don't need much, you don't need, there's not to do much, literally, the straw, other than take the rails, put them in the frame, you cut the strings, you manually adjust them, and that's it. Wow. So there's a lot of opportunity for more technology, but it works.
I really like mechanical pairs. I don't like trying to think the house. Yep. How you accomplish that.
Yeah, so our primary solution there, we build up more. I have to run, but that's like it's a long you're talking about. Same art value, same air tightness, actually higher art value.
That's strong.
No, we're using wood fiber infill. Our floor and roof panels, because the straw is too dense to use horizontally without needing additional structural reinforcement. It's like 9 pounds a cubic foot compared to like the dense timber fills like 3.5 4. So we use that horizontally. And so even with it whistling below the box, it's even as airtight and slate this and use the other stuff. That said, you can totally skirt it or do whatever you want. Our practice is to grade out the soil so it pitches the drain in all directions. Cover it with a subslab membrane and then with a ballast, stone ballast, so that there's no flags of damp, and so that any water that hits there can drain out to the exterior. So I feel a little more comfortable skirting it. But you are then in kind of a crawl space, and kind of those can be a little bit squishy, so you know, there's some building roots in there. But we just make sure that no matter, we don't know what people are gonna do. 2 minutes after you leave, anything. So we just make sure the building can function perfectly well, just up on the piers, and that there's not gonna be a massive moisture traffic on the sides of the lake.
It's